Okay. Get rid of this. All right, so here's the syllabus, and we're on Wednesday, February 2nd. So this is our third week. And so we're going to work on chapter 3 a little more. And then we're going to probably get started on chapter 4. So that's the plan. And then you can follow along. Let's see. Let me pull up the files here. Okay. See, and I think I got to here. Yeah. Okay. All right. So I think I probably need this. Okay. All right. So that's what we're going to do. Make sure on the end of chapter quizzes that you're getting chapter 3, the end of chapter 3 quiz. You should do it by midnight tonight, 11:59. So make sure you do that, and then hopefully, let's see. Let me just stop this for a second. Did you all get an email from your from the TA about when he's going to hold Zoom classes this week? Yeah. So what you should. So I see from Samantha. Yeah. So if you have class that overlaps, then what you should do is talk to him about having at least one session that's scheduled at a time that you can make. So make sure you talk to him about that. So send him an email, and his email address, I believe, is on Blackboard. Let me pull up Blackboard, and we'll just verify that. Let's see. I think I did put it on there. Maybe not. No. Okay. I need to do that. Let me do that. That would be really good.
In the group meet, there were actually quite a few people that had that same concern.
Okay. Yeah. I'm going to put his email. Well, you can. Yeah. His email address might not be in your email because he did it from Blackboard. So I'm not sure what it shows. But let me give it. I'm going to put that on Blackboard right now. So do that. So first I have to do. I don't know why I did that. Okay, that's not what I wanted. All right, let's try this again. Okay, there we go. Okay, and then webmail. Oh, so irritating. Okay. Sorry. I have to have it text me new codes. Okay, 0102244. And then it's Umar. So let me see. Umar. Yeah, okay. And then copy. Okay, and then let me put it on Blackboard. Content. Edit. Okay, so his email is now on Blackboard down near the bottom of the kind of the splash screen. So feel free to email him and let him know that you have a conflict, and ask him to to do one other time this week, so he can cover the homework. Okay. And good. And I probably need to talk to him just a little bit more, so I'll probably send him an email later. All right. Okay, so let's pick up then. So what I'm going to do, let me, I think I'm just going to pick up where we left off. And we were talking about how we take the truth table and convert it into two canonical forms. And I want to talk about that just a little bit more. And let me bring up my projector software here, and then we'll share the screen. Okay, and all right, let me share. Okay, and that's good. Okay, so again, in the combinational design world, everything starts with a truth table, and in the sequential design world, everything will start with a state table, and we'll get to those and talk about those in great detail in the last third of the course. All right, so our truth table, remember we have n independent variables, and we have, say, m dependent variables. So we have 2 to the n rows, and then we have m plus n
We
columns.
can't see.
What's that?
We can't see what you're doing.
Oh, sorry. Okay, yeah, shared the wrong screen. Okay, let me flip that back over. Sorry. Okay, now you should be able to see that. Is that good?
Yes, we can see
Okay.
it.
So our truth table, we have n independent variables, m dependent variables. Therefore, we have 2 to the n rows in the truth table, and we have m plus m columns. So let's do one with where we have 3 independent variables, so n equals 3, and we have m dependent variables. We'll just have 1, so m will equal 1. So we're going to have then 8 rows and 4 columns. So we'll do A, B, C, and we'll do F. And so we for all sorts of reasons, we order these rows in a binary order. Now, sometimes when we do a state table, we'll construct a state table in a non-binary order to begin with, and then we'll reorder it in binary order so that we can use it with our other tools. But we pretty much always want to have it in binary order. And so I'm going to just start with binary order. Normally, the truth tables, we almost always start that way, but sometimes with state tables, we don't. Okay, and then again, I'll put in just an arbitrary F, and usually I like to divide it up into pairs of rows. And it just makes it easier to keep track of what's what. So we'll just do 1, 1, 0, 0, 0, 0, 1, 1. All right, now, remember that we talked about the 2 canonical forms, SOP and POS. And you just need to make sure you got those down really, really cold. The SOP has input layer of AND gates and 1 output OR gate. And the POS is just the other. It has 1 input layer of OR gates, and it has an input layer of some number of OR gates, and 1 output AND gate. All right. And we construct this one with the min terms, and we did construct this one with the max terms. And we have our shorthand notation. So if we do our shorthand notation for the min terms for the SOP form, we would say F equals the sum of the little m's and we number the rows. So this is row 0, 1, 2, 3, 4, 5, 6, and 7. And you can actually, let's see, something happened. Oh, these should be ones. I was thinking. So you can look over here, you can see 1, 1, 1, that's 7 in binary. So the numbers, if you take this as a binary number, it exactly matches the numbers for the rows. Remember, we always start with 0 at the top and we finish with 7. All right, so our midterms then are 0, 1, 6, and 7. All right, and it looks something like that. That's our shorthand notation. And our shorthand notation for the max terms would just be F equals the product of the big M's 2, 3, 4, 5. Now notice there are no cases where a min-term number appears in a max term notation, or a max term row with an output of 0 fits it, goes into the min-term shorthand notation. And then if we write the expansion, then for the min-term, then F is just going to be equal to this row, the min-term for this row, the min-term for this row, the min-term for this row, and the min-term for this row, all ORed together, which that will symbolize that with addition, even though it's not addition, it's ORing. So the first one would just be, because it's 0, 0, 0, it's A prime, B prime, C prime. A prime, B prime, C prime, plus A prime, B prime, C, plus this row. What would this row be? Somebody tell me what that row would be.
The circled one?
No, the one above it.
A prime, A, B prime, C prime.
So it'd just be A, B, C prime, because this is supposed to be a 1. Sorry.
Oh, it looks like a 0, sorry.
Yeah, but pretty good. A, B, C prime, my fault. And then tell me about the last row. What would that one be? Circle one. That's a 1 as well.
A, B, C.
That's right. Good. Okay, you got the idea. So that it's very straightforward, a little confusing. And then what we normally do, we would use some method to simplify this expression. So we would get it in its minimum form. Now, if you use switching algebra, you're never really guaranteed that you're in a minimum form, because it might depend on how you go at it. You might wind up in a non-minimum form. But if you use a K-map, which we're going to introduce after our first midterm, you can see, as long as the number of variables is reasonably small, like 4 or 5, at the most 6, you can do a pretty good job of simplifying it. If you have more variables than that, then you need another technique, and we'll talk about some of those. Let's see. Hang on one second. Somebody at the door. Hold on. Okay, sorry. My wife's out of town, so it's just me. Okay, so this is the min-term expression that's unsimplified. And let's do the max term. So that would be F. Now, remember, these terms, each of these is an and term. And this whole expression is ORed together because of these plus signs. And of course, in here, we imply multiplication. We don't write it, but we imply it. Okay, so the max term expression is just the opposite. So in this case, we're going to have a bunch of and terms multiplied or anded together. So it's going to look like, so the first row is this one because the desired f is a 0. So we need this max term. Well, the max term is the opposite of the min term. And so the max term is going to be a plus b prime plus c. Times a plus, a plus b prime plus c prime. Times a prime plus b plus c. And finally times a prime plus b plus c prime. Again, we have four OR terms here, and they're ANDed together. So this whole expression is just one big AND gate with 4 inputs, each one coming from one of these OR gates. Okay, so that's our canonical expression, and this is really the most important part to get out of chapter 3. All right, I'm going to switch to chapter 2, and we'll talk a little bit about switching algebra. We're going to introduce all the theorems, and we're going to use those. Then I'll come back and I'll simplify these expressions. So let me pop this down and put this up. All right, can you all see that?
Yes.
Good. Okay. So in chapter 4, I want you to be able to hear the learning objectives. I want you to be able to write out the 3 key theorems for conversion. I want you to be able to write the 3 key theorems for simplification. And I want you to be able to simplify a reasonably not too crazy logic expression. I want you to be able to convert a simple 2-layer and or logic expression using switching algebra to an or and form, and vice versa. And I want you to be able to invert a logic expression using De Morgan's laws. So that's what we're going to cover. And we're going to work on this a couple of periods. Okay. And then we just have one more chapter to cover before we're ready to review for the first midterm. All right. So how to approach switching algebra. So these are some really, I think, important concepts. First off, you have to remember it's not regular algebra. So it looks like regular algebra because they have stolen the concepts of multiplication and addition to represent ANDing and ORing. But it's not multiplication and division. It's ANDing and ORing. So it behaves entirely differently. And there is no such thing as division and subtraction in switching algebra. In fact, there's no such thing as multiplication and addition either, but we just use those concepts to represent ANDing and ORing. We deal only in symbols and not in numbers. Even though we use 1s and 0s, they don't mean the number 1 and the number 0, the value 1 or the value 0. They mean true and false. The fact that variables can only have one of 2 possible values has a huge impact on switching algebra. If variables could have an infinite range of possibilities, then switching algebra would be just like regular algebra and it wouldn't make any sense. But the fact that any particular variable only has 2 possible values, true or false, totally changes how we can do proofs. And also it's what gives us the power to use it in digital design, because in digital design, our signals are basically either true or false. They're either 1 or 0, and we normally represent those by voltages or by currents. There's no such thing as addition, subtraction, multiplication, or division. Just ANDing and ORing, and inversion for that matter. Everything can be proved or disproved. There's nothing that's left unresolved. Okay, so unlike regular math, where there are all these crazy postulates and theorems that, you know, somebody gets their PhD thesis in mathematics by showing there is a solution or there's not a solution, or it's true, it's not true. That's not true in switching algebra. We can resolve every single expression we can resolve to true or not true. Every theorem we can show is either true or not true. And our proofs are really easy. When we have a solution for, say, a truth table, there are often several equivalent solutions, but that are not identical. That frequently happens. It's not always the case, but it frequently does happen. When you do switching algebra, one of the things that the beginning student runs into is they wind up going around in circles. They move in one direction, kind of like this is particularly true when we want to convert from, say, an SOP form to a POS form using switching algebra. They'll start moving from the SOP form towards the POS form, and then after a while they start moving backwards, going back to the SOP form. And when they filled out a whole page of lines of their equations, they find they're back to where they started. Quite frustrating. So you really want to work on keeping in the front of your mind which direction you're going. Are you going from an SOP form to a POS form? Or are you going from vice versa? Before we start converting from SOP to POS, we always want to simplify the expression as much as possible. The theorems that we're going to cover in just a minute are all you can do. That's it. You can't do anything except what's specified in these theorems. There's nothing else you can do, only what the theorems allow you to do. And whenever you work on say a SOP to POS conversion or vice versa, try one approach, try a different approach. Sometimes the way you start out can really make a difference in how easy or difficult it is. And so sometimes backing up and starting over is a really good idea. Okay, so these are just some things to keep in mind. And I encourage you to come back and review this slide after you've worked some problems. All right, and I have another slide with hints on it. Okay, so I break the theorems down into 4 different groups. The trivial theorems that are pretty obvious. And then there are 4 simplification theorems. And then there are the conversion theorems. And I think there's 3 or 4 of those, I forget. I have to think about it. And then there's the inversion theorems, which give us the inverse or another thing called a dual. And we'll see that. The dual used to be used a lot more than it is now, I think. Back when we did schematics and we had different groups working on different parts of a design, and one group would use inverse logic and the other would use positive logic. And then when they wanted to put their designs together, the dual could be quite useful for that. Every theorem, though, does have a dual form. So we do use it in that sense. And then you need to work enough problems so you become familiar with the theorems, and probably should memorize, maybe 4 or 5 or 6 of them. You should kind of be able to just spout off from memory. All right, so here are the trivial theorems. The first one is, and we've looked at, and some of these sort of conform to Hunt's postulates. All right, so the first one is operations with the constants 0 and 1. All right, so if we OR x with 0, we get x. If we OR x with 1, we get 1. If we and here's the dual. If we and x with 1, we get x. And if we and x with 0, we get 0. All right, and if you think about it, that's pretty obvious, right? Since in the and function, both things have to be 1 to get a 1. Otherwise, it's a 0. Well, since this is a 0, then it can never be the and result of whatever x is, or and it was 0 is always 0. And here, we don't know what x is, but if you and it with 1, we know that now the result depends on x. If x is 1, we'll get 1. If x is 0, we'll get 0. So our result is just x. Here, if you OR x with 0, then the 0 doesn't make the output of the OR gate 1, but if x is 1, it will be 1, and if x is 0, it will be 0. So you just get x. And here, doesn't matter what x is, if one of the inputs is a 1, the output's going to be a 1, because that's how an OR gate works. Then the in idempotent operations, basically x ORed with x is x, x ANDed with x is x. And here's the commutative. It doesn't matter the order. X ORed with y in that direction is the same as y ORed with x. Same thing here. And then complements. If we OR x with its complement or its inverse, we'll always get 1. But if we AND x in its inverse, we'll always get 0, because one of these is going to be 0. If x is 1, x prime is 0. So the AND of 1 and 0 is 0. Here, one of these is going to be 1. So your output's going to be 1. And then this associative law, again, this applies to AND gates and OR gates, but it doesn't apply to NANDs and NORs. And then we have the double inverse. If we take x and invert it, and then we invert it again, we're back to x. And there's no dual of that. So, okay. Any questions about these? I'll pause here a second. As you look at those, do those pretty much make sense to you? All right, I will assume the answer is yes. Okay, they are pretty straightforward, but you keep these in mind because you'll use these. These are very helpful. So like if you have x times x prime in your expression, you can just drop that term completely because you know it's 0. Unless it's one of your AND gate inputs, then you need to keep it, but whatever. All right, so anyway, so simplification laws and theorems. So these are the 4 theorems you use to simplify an expression. And you should do this first. If you can simplify the expression by combining terms, eliminating a literal or eliminating a term, or using the consensus theorem. Now, on the consensus theorem, this is a little tough to see when you're working problems. So we kind of leave this alone until we get to K-maps after the first midterm. And then when you look at a K-map, the consensus term makes so much sense. So I kind of leave it for then. But you should look at it. But I'm going to try and avoid giving you problems where you have to use this theorem. Now, it turns out there are plenty of problems where you can use this theorem, but you don't have to use this theorem. And some of the problems may be like that. But yeah. All right. So these 3 are the ones to concentrate on until we get to K-maps. So combining terms. So we're going to use, this is S1. We're going to use S1 extensively. And usually when we try and simplify from a truth table, this is the simplification theorem that we use. When we convert from SOP to POS, we might use these others, but this is the one we use when we're trying to simplify the truth table. All right. So we take XY plus XY prime. You can combine these and just have an X. So because the Y changes, it basically drops out. And if you think about it, this expression XY plus XY prime doesn't depend on Y, because here you have, let's say Y is 1. Okay, so in this case, X times X ANDed with 1 is going to be X, and X ANDed with 0 is going to be 0. So X ORed with 0 is going to be X. If you take the other case where Y is 0, so then this term would be 0, but this term would be X, because that would be X ANDed with 1. And then you'd have 0 ORed with X, which just becomes X again. And the same thing here. That's the dual. So if X is ORed with Y here, say Y is 1, okay, then that just results to X. Sorry, if Y is 1, then this expression results to Y, to 1. And then that's 1 ANDed with X ORed with 0, which just is X. So that's 1 ANDed with X. And we know from this, 1 ANDed with X is X. Okay, so it's easy to see that these are true. Here, this is a little trickier. X plus X prime Y is just X plus Y. This X prime gets dropped. Now, why is that? Well, let's say that X is 1. Okay, if X is 1, then this expression resolves to 1, and this term doesn't count, doesn't really contribute anything. If x is 0, then this first expression goes to 0, or this first term goes to 0. So it's 0 ORed with whatever this is. And since x is 0, x prime is 1. So now this term just becomes y. So you can see that if x is 1, it just depends, it depends on x. And if x is 0, it depends on y. So that's x is y. And the same thing here. If we and x with x prime ORed with y, we just get xy. This, we can drop this x prime. This is this can be tricky to see. You know, you'll find that there'll be many expressions where you can drop one of these variables, but it'll be hard to know if that's true for sure. You'll kind of stare at it and wonder. And you know, I think it takes a long time to be able to apply this one efficiently. Okay, eliminate a term. This is pretty straightforward, and this can be very, very helpful when you're trying to convert from SOP to POS. So here we have xy plus x. Well, because if x is 0, so this term goes to 0, and this term is 0, so it just basically is 0, which was x, which is what x was. If x is 1, this term is 1. Doesn't matter what this term is, it'll still be a 1. So it clearly just depends on x. This term can be completely dropped. Same thing here. And then finally, the consensus term shows that this term, so we have xy plus x prime z. This term zy right here, the yz term, doesn't add anything. And and the same thing here. We have x plus y, x prime plus z. So what we have to see is an x and an x prime, or some variable in its prime to make this work. And then this yz term, y ORed with z term, doesn't add anything. This is a little tough to see. Like I said, when you see it on a K-map, it's obvious. When you try and see it in algebra, it's a little confusing. So don't spend a lot of time on the consensus theorem. Just look at it, and if you want to work on it, that's fine. That's up to you. But it'll be a lot easier to digest this when we get to K-map. So that's why I usually leave it for that. Okay. That's the simplification theorem. And then finally, we have the conversion theorems. And they're two distributive laws and then one multiplying and factoring theorem. So there are really three theorems here. The first distributive law we call C1. The second distributive law we call C2, or second distributive law. And the third one we'll just call C3, or multiplying and factoring. The first distributive law is very much like regular algebra. You can have x ANDed with y ORed with z, and you can distribute the x in here. So that's the same as x ANDed with y ORed with x ANDed with z. And the second distributive law, and this looks like regular algebra, so it's easy to visualize this. This one, on the other hand, is absolutely not true in regular algebra. This is completely invalid, not true at all in regular algebra. But in switching algebra, it's fine, it's true. What it's saying, maybe I'll work through a proof of this. But if you have x ORed with yz, that's the same as x plus y quantity times x plus z. And it is also true. Let's see. Oh, did I kill it? Oh, no. It's also true if you have so here we have x plus yz equals x plus y quantity times x plus z. It's also true if you have x plus wy z. That is x plus y quantity times x plus z quantity times x plus w. So it just adds that one more term. So this is a good extension of the second distributive law to remember, because that may come up on a test. Okay. All right, so note that the first and second distributive laws are the duals of each other, for what that's worth. All right. Now we talk about inversion and duality. So De Morgan's laws are the names we give for our inversion. Now the simplest form of De Morgan's law is just to take to invert x, we just invert it by putting a little tick. Now I know a lot of notation uses a bar, and there's other notations as well, but we're going to use this because it's a lot more printer friendly. Okay. So if you have a more complicated expression like this one, so the inverse of x, y, z, so that's x ANDed with y ANDed with z, is x prime ORed with y prime ORed with z prime. And here, if you have x ORed with y ORed with z and you invert that, you get x ANDed with y, x prime ANDed with y prime ANDed with z prime. The dual, and we'll look at this. One of the things though, with using De Morgan's laws to do the inversion here, you have to preserve the order of precedence. And I'm going to show you where that can get you into trouble. And we need to avoid that. With duality, we use a superscript d here for the dual. And so the dual of x, y, z is x plus y plus z. Now, what's the difference between inversion and duality? In this case, we only invert the operator. We don't invert the variables. So we invert the and here to an or, but we don't put primes on it. And that's the dual. Same here. We're going to invert this. I mean, we're going to create the dual to this. So we invert the operators. We take the ors to ands, but we don't put the primes on. Now, again, we're not going to really use duality at all in this course, except that we have the duals of our basic theorems. And that's about the only time we'll ever use the dual. So I don't care that you spend a lot of time thinking about the dual. Like I said, it's not really in practice used all that much, but you should know about it. Go ahead, question. Angel, did you have a question? Okay. Yeah, feel free to ask questions anytime. All right. So again, the dual was used to convert from negative to positive logic, something we kind of did in the past, not anymore, or not much. So here are all the theorems together. This is figure 4.2 in the book. And so the trivial laws, the simplification theorems, S1, S2, and S3, the consensus theorem, S4, we'll kind of leave for later. The conversion laws, the first distributive law and the second distributive law are C1, C2, and finally the multiplying and factoring theorem are C3. Let's see. I don't think we covered the multiplying and factoring theorem, did we? Yeah, we did. Okay, yeah, we did. Got it. Okay. And then finally, De Morgan's laws and duality. All right. So, so here's an example of proving the second distributive law using a truth table. And so it's probably worth going through this. So maybe I'll just take the time to do that. All right, so let me pop this up. So so let's write the second distributive law out. So we have x plus yz equals quantity x plus y times quantity x plus z. All right, so how are we going to prove this with a truth table? Well, what we're going to do is we're going to construct a truth table with 3 independent variables. So n equals 3. So it's going to have 8 rows. And then how many columns are we going to have? How many dependent variables? Well, we're going to use all these expressions as our dependent variables. So we're going to use x, we're going to use y AND with z, and we're going to use x ORed with y AND with z, and then we'll use x ORed with y and x ORed with z, and we'll use them ANDed together. So we'll actually have 1, 2, 3, 4, 5, 6 output columns. So we're going to have plus the 3 variables, so we'll have 9 columns. Okay, so let's do that truth table. Flip it around here. So our independent variables are A, B, C, or sorry, X, Y, Z. Okay, we'll do X, Y, Z. And then our dependent variables are going to be each one of these figures. So we'll have a column. I won't do a column for X because it's right here anyway. So let me write these in. And we'll do them in pairs here. Now we're going to do a bunch of columns though. All right, so my first column, I want to do X, but I will make my first column YZ, okay? So Y ANDed with Z, so we'll do YZ. All right, so let's figure YZ. So Y ANDed with Z, so 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 0 with 0 is 0. 0 with 1 is 0. 1 with 0 is 0. And 1 with 1 is 1. All right. So that's that one. Oh, maybe I'll throw the X in. What the heck? So X is just 0, 0, 0, 0, 1, 1, 1, 1. All right. Now, let me OR these two columns together. So we're going to OR this column with this column. So this is going to be X or YZ. Okay, so X or YZ, well, 0 or 0 is 0. 0 or 0 is 0. 0 or 0 is 0. And 1 or 0 is 1. 0 or 1 is 1. 0 or 1 is 1. 0 or 1 is 1. And 1 or 1 is 1. All right, so that takes care of this side of the equation. We're done. Okay, let's do the other side. So we're going to have X ORed with Y, quantity. So X or Y. And then we're going to have X or Z. And then we're going to have the quantities together. We're going to have X or Y, quantity ANDed with X or Z. All right, so X or Y, well, here's X, here's Y. They're both 0, so that's going to be 0. Both 0, so that's going to be 0. Y is 1, so these are going to be 1s. And then from here on down, X is 1, so we know all these are 1s. Same with here, X or Z. So this will be a 0, but here this will be a 1 because Z is 1 there. Here, Z is 0 again, so X and Z are both 0. But here Z is 1, so that's a 1. And then here, X is 1 for all these, so it doesn't matter what Z is, it's going to be 1. And now we just have to AND these two together. So 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. And 1 ANDed with 1 is 1. 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 And 1 ANDed with 1 is 1. Now, once we get to this point, how do we know if we've proved our relationship? Well, again, our relationship is X plus YZ equals X plus Y quantity times X plus Z. All right, so what column corresponds to this one? that one. And what column corresponds to this one? That one. So if these two columns are the same for every possible combination of all of our independent variables, then we've proven that this side always equals this side, therefore it's true. If, on the other hand, that's not true, then we've proven that it's false. Well, so are these two columns identical? Well, obviously they are. They are exactly the same. So as a result, we've proven that this second distributive law, or C2, is true. All right, is everybody good with that? Any questions about that? All right. So it's pretty straightforward. Okay, what about the multiplying and factoring theorem? Well, we did the same thing here. So the theorem, the original theorem is down here. Xy plus x prime z equals the quantity x plus z times the quantity x prime plus y. Now, let me show you how we normally write that. It's not super complicated or anything, but we normally write it just a little bit differently. So x plus y times x times x plus x prime plus z equals, and what we do is we take this x and we match it up with this z, and we take this x prime and we match it up with the y, and we use these little bracket things to keep it straight. So now we know that it's going to be xz equals x prime y. I'm not equal, but plus x prime y. Or if you want to go the other direction, we take the x and we marry it with the y. We take the x prime and we marry it with the z. Now you can write it, if you want to write it x prime plus y, quantity times x plus z, it's the same thing. You've just switched the x, and now you marry the x prime up with the z and the x up with the y. And you get x prime plus z, I'm sorry, you get x prime z plus xy. So the primes can move around. That's fine. You just have to keep track of them. There's no, I guess this is, I don't know if this is how we normally write it, but it doesn't really matter. All right. So to prove that, then we would do the same thing that we did with the other truth table. You can see here, so we did x ANDed with y, get this column, x prime ANDed with z, we get this column, and then x prime ORed with y, we get this column, x ORed with z, we get this column. Now what we have to do is we have to OR these two columns and these two columns to get this column and this column. And it turns out these columns are exactly the same. So for instance, if we AND these two, that's going to be over here. I'm sorry, if we OR these two. So 0 ORed with 0 is 0. Okay, there. 0 ORed with 1, 1. 0 ORed with 0, 0. 1 ORed with 1, 1. 0 ORed with 0, 0. 0 ORed with 0, 0. 1 ORed with 0, 1. And 1 ORed with 0, 1. And we do the same here, only we're going to AND these two columns. 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 0 ANDed with 1 is 0. 0 ANDed with 1 is 0. And 1 ANDed with 1 is 1. And 1 ANDed with 1 is 1. And notice they're exactly equal. That proves that for all possible combinations of the independent variables, both sides, this is one side of the equation, this is the other side. Both sides always result to the exact same result. Therefore, they're always equal. Therefore, it's true for every possible combination of X, Y, and Z. Okay, so that's why it's really easy to do proofs in switching algebra, because you can look at every possible, all possible values of the variables, assuming you don't have an infinite number of variables. And in the digital world, we never have an infinite number of variables. it's always finite, maybe large, but it's finite. So we can always sort these things out. All right. So remember our canonical forms. Any logic expression can be put in these forms, and every truth table can be represented in an SOP or POS form. And you can always convert from one to the other. Now, you might not be able to do it because it can be difficult in some cases, but it's always possible. And these forms can be used to prove that the two sides are equal. So another way you can prove two sides is you can use switching algebra, say in this case, and you can convert this expression using switching algebra into this expression. All right, so, and yeah, maybe I'll do that in a minute if we have time. All right, remember that we call and terms are called product terms, which it means we're implying anding with multiplication. So it looks like A, C prime D or something like this. We call R terms are called sum terms, which implies ORing. We use the plus sign to imply ORing, or we're using addition to imply ORing, but it's not addition, it's ORing. And that would give you something like A prime plus B plus D quantity. We usually put these in quantities because then we're going to multiply this whole thing times another sum term. So that's why SOP is and OR, and POS is OR and AND. And then, so here's an example. This is the SOP form. We have all these AND terms ORed up. This is the POS form. We have all these OR terms ANDed up. So in this case, we'd have 1, 2, 3, 4 input AND gates, 1 output OR gate with 4 inputs. And here we'd have 3 input OR gates, these two with 2 inputs, this OR gate with 3 inputs, and then 1 output AND gate with 3 inputs. All right, so now I'll do some examples. Let's see, we got time maybe for one. I think we're probably just about out of time, but I'll do one example. But before I do it, let me just ask if there are any questions. Did anybody have any burning questions? Okay, so let me do this one example. All right, so let's say we want a factor to get 4 product terms. We're going to take, so somebody tell me, what form is
Can
this
you
in?
share your screen?
Yeah, sorry. Yeah. Share the correct screen. All right, somebody tell me, what form is this in now? Is this in SOP form or POS form?
SOP.
Yes, it's SOP. Is that what you said?
Yes, sir.
Yeah, okay. Yeah, very good. And how many terms do we have?
Or
And how many gates are represented here by this expression?
well, it's 4 ORs and 1 AND.
So there's 4 input AND gates and 1 output OR gate. So there's 5 gates involved. Right?
Yes, sir.
Okay. So we want to change this into POS form, and we call that factoring. When we change POS to SOP, we call that multiplying out. Again, these are horrible terms because they're confusing, but that's how the literature reads. All right, so the first thing to do, we look and see if there's any of these terms that we can combine or use one of our simplification theorems. So if we back up to our simplification theorems, do you see any simplification theorem, especially the first 3? Don't worry about the consensus theorem for now. But do you see any way you can apply either of these? We'd be going from the SOP form to the POS form, so we'd be using this column. Do you see any of these that we could use? All right. So can we combine terms? Can we eliminate a literal? Can we eliminate a term? So let's go back and look. All right. So does anybody see any of those rules that we could apply here?
A is a changing term.
Well, that's right. So A there's an A prime, an A prime, and an A. So in every one of these groups, we have a variable, the A variable is present either in its prime or non-prime form. So that's true. That's a good observation, but that's not helping us at this minute. So what could we do? Well, one thing we can do, notice we have A prime, B prime, D, and here we have A prime, B, C. Can we do anything with that? No, probably not. And then here we have A, C prime, D prime, and here we have A, C, D. No, can't really do much with that. So what we can do then is we can use the first distributive law, and we can rewrite this expression, and we can factor an A out. So let's see. So let's see what we do. So we use that first distributive law, and we'll group ACD and AC prime D prime, and we'll factor the A out, and that'll give us A ANDed with CD ANDed ORed with C prime D prime. And then we'll factor the A prime out, and we'll get A prime ANDed with B prime D plus BC. All right, so that's just using the first distributive law. So we couldn't really simplify it, so that's fine. So now we take the first distributive law. Now we can do a couple of other things. We can simplify what's inside here using the multiplying and factoring theorem, because we have a CD plus a C prime D prime, and we could actually pick either one of those. Here we have a B prime D and a BC, so we could use B prime and B and the multiplying and factoring, or we could use the multiplying and factoring with the A times this plus the A prime times that. So either way, let's do that. So we're going to apply the multiplying and factoring to what's in the bracket on this side and what's in the bracket here. So we'll apply it 2 times. And now we get A times C plus D prime times C prime plus D plus A prime times B plus D times B prime plus C. All right, so let me just yeah. So we use the M and F 2 times to do that. Let me see. Let me write this down and then I'll switch. So we got to A times CD plus C prime D prime plus A prime times B prime D plus B C. All right, so let me switch and then I'll just go through that so you see that. All right, so we applied the multiplying and factoring here. So we took the C and married it up with the D prime and the C prime and married it up with the D. So that gives us C plus D prime quantity times C prime plus D. And then we still have to have A times all that. Plus, now we have the A prime, and we take the B prime with the C and the B with the D. And so that gives us B prime plus C quantity times B plus D. Now, notice what I'll usually do when I do this is I'll write out the multiplying and factoring theorem, and I'll put an arrow over the top of it to show how I'm applying it, to make sure that I don't get it all confused. And in this case, let's write out the multiplying and factoring theorem. So multiplying and factoring theorem, I have it up here. So it's x plus y times, actually, we're going in the other direction. So let's write it this way. It's, let's say, xz plus x prime y equals x plus y quantity times x prime plus z. Now, so we're applying it in this direction. Now notice we have this set up here. We still have an A and an A prime, so we can apply the multiplying and factoring one more time using A. We'll marry the A up with this whole business here, and we'll marry the A prime up with this whole business here. And so that's going to give us A plus this B prime plus C times B plus D. And it's going to give us Yeah, and all this now is multiplied by A prime plus this business, which is C plus D prime and C prime plus D. Now you have to remember, we wind up with a multiplication here because here we have it's ANDed. So same thing here. We're starting with this and we're going to this. So that we wind up with this quantity times this quantity, or we had this quantity ORed with this quantity. We have this ORed with this, and now we have this ANDed with this. And now we're in now we have a couple of things we can do. We still have A plus this times this, so, and A prime plus this times this. So what we can do is we can use the second distributive law, and we can take this can be our X, this can be our Y, and this can be our Z. And here we can have, this can be our X, this can be our Y, and this can be our Z. So we'll first apply the second distributive law to this part, and we get A plus B prime plus C quantity. What question? Times A plus B plus D times A prime plus C plus D prime times A prime plus C prime plus D. And now we have, it's in pure POS form. So that, if we, so we'll do the M&F one more time, which we did, and then we'll use the second distributive law twice, and we get those four terms. All right, so that's a fairly complicated example, not particularly super easy to do, but this is about as difficult a problem as I would ever give you. All right, so I'm gonna end with that. So make sure you do the quiz for chapter 3 by midnight tonight, and otherwise we'll I may do I'll hopefully do a video for you on Friday live, but I may do a pre-recorded one. And if I do that, I'll send out an email and give you the link, and also put the link in Blackboard under in the video. I will, as soon as this video is rendered, I will post it. It takes a while for it to get rendered. All right, any questions? All right, we will see you later.